Okay, so learning module 3, fundamentals of electrical circuits. This unit builds upon what we've seen in the previous units. As I mentioned, we're going to be doing a lab exercise in the laboratory where we're going to be working with some electrical components. We're actually going to make a circuit and you're going to do measurements and all that. But that is going to be a lab exercise in the lab. That isn't with anything that you need to get or have by yourselves. This is what you guys did, what I asked you to research. And so you already researched some of the concepts we're going to be seeing here at the beginning. So jump in if you remember something, or maybe while you were researching anything, if you have if any questions came up. So one of the, I would say, most important and fundamental laws in electrical circuits is Ohm's law. Okay. And Ohm's law basically relates three things that are very important for any analysis or design of an electrical circuit. It's three things. And we're going to be talking about these three things from now on. One thing that's very important in this learning module, or starting this learning module, in the previous learning modules, I'm sorry, the electrical charges were static. They were not moving. So in learning module number 1, it was electrostatics. We talked about the forces and the electrical fields having to do with charged particles or objects. Then in learning module 2, we talked about capacitance, which had to do with storing electrical energy. But in those two learning modules, the electrical energy, or rather the electrical charge, was not moving. So imagine the concept of having, again, we're going to be trying to link this as an analogy to fluids from now on. So whenever we talk about electrical charge from now on, think about a fluid, water, or any sort of fluid. So the fluid, or the H2O molecules of the fluid, those are the charged particles. And if I fill up, and those aren't moving, they're static. A container, I can fill up a container with water. That's the analogy of a capacitor. The water is there, but the water isn't moving. It's stored. Okay. From now on, we're going to be looking at what happens when charges start to move. And this links to something that I told you guys to think about as mental gum. We have something called electrostatics, right? But we don't have something called electrodynamics. Why? Because the moment charges start to move is when we start to talk about electrical circuits. Okay. And so Ohm's law is a very important part, or a very important law that relates three things. It relates voltage. We already talked about voltage. We know that voltage has to do with the energy required to move something, to move a charge. However, previously, when we talked about voltage, it was like potential energy. Remember that in dynamics about potential energy? I'm not going to draw up my cell phone again. So potential energy is if I'm holding the cell phone on top of the table, that's the potential of energy that is required for me to hold it there. Once I let it go, the potential energy turns into kinetic energy, which is the movement. Voltage is the same thing. When we're talking about voltage, having to do with the potential or energy required to move something. Now the voltage is going to be the energy that's moving the charges. So that's one of the things that have to do with Ohm's law that's important. The other is the concept of electrical current or electric current. Okay, we'll talk about that in a minute. And the third thing is a concept called resistance. Okay, so Ohm's law is going to relate those three things, and there's a triangle there. So that triangle relates to Ohm's law. And we're going to be doing something from now on at the beginning of each class that I've done previously in the other classes and the other groups, which I assume aren't less uptight or more fun than you guys. That's what I said. They're not less uptight or more fun than you guys. And they understood it and they liked it and we did it. So this is part of the weird things that we're going to be doing, but hopefully it's going to help you remember Ohm's law from now on and until the day you leave this existence. So what we're going to be doing at the beginning of each class is that we're going to do a small exercise where we're going to try to eliminate any and all negative vibes and feelings and emotions and thoughts from us. So we can start off the class in a relaxed way, and we're gonna leave everything behind. Okay? And we're gonna do this small exercise, and I'm gonna ask you to do it. So you're not too. So this is good because Diego just put on his cool glasses, and that's good because the exercise. No, leave them on because the exercise has to. The cool glasses are gonna help out for Diego. Oh, you better. The exercise is actually gonna help the red sunglasses help out with the exercise. So what we're all gonna do is the following. Okay. Grab your hands and you're gonna make a triangle. You're gonna make a triangle. However you want to make the triangle. Okay? And you put the triangle in front of yourselves on top, however you want. You're gonna relax. You can do this with your eyes open or eyes closed, however you wish. You're going to relax, and everybody at the count of 3, we're gonna say Om. Okay? Which has to do with, we're not gonna say Om's law, we're just gonna say Om. Okay? And we're gonna remember Ohm's law. Okay? So at the start, and when you do that, all of the negative energy has to go out of the triangle and out of the atmosphere, and it goes away. Okay. So everybody, 1, 2, 3. That was really extremely flat. It was really flat. Let's do it again. Let's do it louder. Let's make the other classrooms say what is happening in this classroom. Okay, let's do it a little bit louder. Really get things out. Okay, so Yesenia, you're not going to get the bad energy out if you're looking at these sets of beats. 1, 2, 3. Okay, and that's Ohm's triangle. We're going to be talking about. So Javier got like in the fixed position. You stay that way, and that's fine. If it helps you out, at some point in the day, just close your eyes and go like that. And so we're going to be remembering Ohm's law at the beginning of each session. And there's a few other laws in magnetism where I'm going to be making you do things with your hands and stuff. So that'll help you remember. So Ohm's law is going to be this triangle Ohm that relates these 3 things, and that's what we're going to be talking about today. So first off, let's talk about the first thing, voltage. We already talked about voltage in the previous unit, and it was this electrical potential. Remember the weird definition or long definition that we gave? Voltage was the energy required to move a positive charge from infinity to point A against an electrical field. And that only meant that if we made the water analogy or the fluid analogy, if we have a river and we're grabbing a rock and we're trying to move that rock against the river, there's a certain energy value. Now imagine that I'm moving the rock not from infinity, but from point A to point B. There's a difference of energy I need to move things from one point to the other. Well, that concept, we're going to take it now to electrical circuit, and it's going to be the same concept. It's going to be called voltage. And it's the measure of energy I need to move a charge from one point to the other. Okay, that's what we call voltage. Now I'm going to ask you a question. Let's see. Let's talk about physics. I've got this water bottle right here, and is it clear that the water or whatever fluid I have in here it is water? It's static. It's not moving, right? A little bit. You can pass it around. I have no. I don't want to. I'm not going to get fired for that. So no, you can. No. That would take terrible. No. So the water isn't moving, right? What makes water move or flow? Well, good. I thought you guys were going to say that. No, let's say I leave it here. and I'm just putting the example of the bottle, but in general, what makes water flow from being static to moving? Pressure. Pressure, and pressure has to do with gravity. But correct, it's very simple. What makes water move? Pressure. There's a point with more pressure and a point with less pressure, and that difference makes the water move, and it does have to do with forces in gravity. Okay, so what would make this water here move if I grab an ice pick and I pop it, and then suddenly there's a difference in pressure from the top to the bottom, and what's going to happen? Water is going to start flowing. But right now, there is no difference. There's nothing that's generating that difference, okay? So I want you to keep that in mind, because in electrical circuits, voltage is analogous to pressure, okay? If I want water to move, I need a pump. I need something that generates pressure. In an electrical circuit, if I want electrical charges to move around the circuit, I need a pump. I need something to generate that. That is a voltage source. What is a voltage source? A battery. Any sort of battery is a voltage source, and it's going to be that device that is going to make charges move. Okay, so always relate. Voltage is related to pressure. Okay, with that analogy. Now, what is electrical current? Well, the concept of electrical current is really, really simple. Oh, just remember, voltage, obviously, we already saw it's measured in volts. Okay, it's volts. What is electrical current? The concept is very simple. Before, charges were static. Once a charge starts moving constantly, electrical current is the rate of that movement. So I have a certain amount of charges moving by a certain amount of time, okay? Meaning I have 10, I have an object, I have 10 microcolumns, or I have a flow of 10 microcolumns per second. That means that if I look at any point, 10 microcolumns are flowing by that point every second. So it's the amount of charge, or it's the rate of flow of charge, okay? The unit of measurement is the ampere. I was confused as to how to pronounce that in English. In Spanish, it's very easy. It's called ampere. I think in English it's ampere. Ampere. The E is kind of compressed, so it's kind of like just ampere. Yes.
That's the same direct current and not current, right?
Yes, I have a driving step, but yes, yes. So the units are amperes or amps. They're also called amps. And the amps are going to be that rate of flow. So if I have a voltage source or a power source that's generating a voltage, that difference in voltage, always the power, if you grab a battery, there's a positive terminal and a negative terminal, right? That's that difference in voltage. So they're going from one point to the other. The electrical flow of charge, that is what's called the electrical current or electric current. Somebody asked me when you were doing the work on last class, you asked me, it's the same if you talk about electric current and electrical current, they're analogous, they are the same. And there's two types of electrical currents. What's called DC and AC. You've probably heard the AC and DC concepts. AC/DC? AC/DC is a band. AC/DC is a rock and roll American band, right? No, they are Australian. They're not American. They sound American, but there are a lot of rock and roll bands that seem very like American, but they're not American. AC/DC isn't American. Black Sabbath is an American. Deep Purple, a bunch of Pink Floyd. They're not American. So what does AC/DC mean, or what is that concept, or what is that? It's alternating current and direct current. That's what the A and the D mean. By the way, I just want to mention this because somebody might ask the question. For some reason, there are certain guidelines or certain, how could we call it? Yeah, certain ways to name things and identify things in electrical circuits. So somebody at some point said, we're going to differentiate between direct and alternate with regards to the current. So there's alternating current and direct current. But we could also have alternating voltage and direct voltage. It's actually related. But AC/DC sounds much better than AV/dV. Okay, so you don't see alternate voltage or direct voltage, but it's the same thing. If I have direct current, it's probably because I have direct voltage. If I have alternate current, it's because I have alternate voltage. The two things are related, but the concept of alternate and direct are named with regards to current. Now, what is the concept of alternate and direct current, or the two classifications? Direct current, I'm going to do some exercise just to explain, but that's not going to be in the video. This is point A, and that's the door is point B. So direct current, I'm the electron. I'm always going to be moving from point A to point. I'm always going to be moving in one direction. I'm moving in one direction. That's why it's called direct current. I'm always moving in one flow. One flow in one direction. Alternating current is generated when the movement of the electrons is, I'm going in one direction, and then I go back. And once I go back, I go forward, I go back. Alternating current, it means that you're going from the current is flowing in one direction, then at another moment, the current is flowing in another direction, then one direction, then another direction. It goes back and forth. Now, some of you might be asking, but why? It's really, that would be really weird. Why would current do that? Well, it actually has to do with the ways in which we generate electricity. So for example, the current that's coming out of the wall socket, is that alternate current or direct current? It's alternating current. So if the current that's coming out of the wall socket is alternating current, it's going up, down, up, down, up. If we were to graph it, it would be a sine wave. What type of current does your computer need to operate? In direct current. What type of current does your phone need to charge? Direct current. Because of the size, because of the type of components, it's most things are going to need direct current. So what do the little boxes do that connect between the computer and the wall socket? There's a box. When you connect the iPhone or whatever phone to the wall socket, there's a little box. What does that little box do in whatever connection we have over here? It's converting alternating current into direct current. That conversion process and all that, we're not going to see it this course. That's a topic for industrial electronics next course. There's a process to convert. Okay. There's a process to convert it. Now, why does alternating current exist? Because the way we generate energy automatically generates alternating current. And we're going to see that a little bit more in the magnetism unit. But basically, this drawing that's here, this is a magnet. This is a magnet, a north and a south pole of a magnet. And if I put something there in the middle that's metallic, and I can change its polarity, I can generate movement. And I don't know if maybe in high school or at some point you talked about, or maybe you have to construct a motor, or an electrical motor with magnets. It's a very simple thing you can do. But the curious thing is a motor generates movement. But if I grab the same concept of a motor and put it on a wind turbine, the movement of the turbine is going to generate electrical energy. But because of the construction of generators, automatically the polarity is changing. And that's why when we generate electrical energy, we're generating alternating current. But the devices we use, those need direct current. And so there's a conversion process. Right now for this course, yes.
Which ones were the ones, the motors?
Well, there's alternating current motors and direct current motors. You can use, and there's any of those. But the basic concept of a motor is that you have a magnet with two polarities, and you have another magnet inside that's changing polarities. So since the same polarities are gonna repel each other, when you've got north and north and south, it's gonna flip. And then if I flip it again, it's gonna move again and move again, and that's what generates the perpetual motion. Now, if I invert that, and you can actually do this, well, you don't need to do this test, but if you can grab any motor, and maybe, yes, maybe we are actually gonna be able to do that exercise in the lab. You can grab any motor. For example, you can grab a toy motor from a toy car or whatever. If you grab the shaft of the motor and start turning it with your hands and measure with a multimeter, you're gonna see that there's a little current going out. And if you move it more faster, there's more current gonna be flowing. And so that's the way we generate electrical current. Basically, how do we generate electrical current with water? Well, we've got a wheel or some sort of turbine, and when the water hits it, it's turning around. And by turning around, we're generating this polarity and we're generating the current. How do we generate current with steam? It's the same thing. Instead of the water moving the wheel, steam is moving the wheel.
That's like the steam engine.
Like the steam engine or the thermoelectric plants, for example. And so there's going to be these two types of current. Right now, for this course, in the exercises and examples we're going to be seeing, we're just going to be talking about direct current. We're not going to be seeing alternate current examples. Those are for next semester.
I'm wondering if this is related to what you're saying, but if you see that in the Coldplay concert, there were like stations where you could be in a bicycle and that energy was used in the concert.
Oh, that's a dynamometer. Yeah, basically.
What do you think again?
There were people from the crowd, like volunteers, that were in bicycles and
Generating the energy.
creating energy for the concert.
They can hire it. They can hire you for that. But yeah, okay. How many kilowatts? How many kilowatts hours do you want? Maybe not. That basically just said that you're mentioning is the concept I was talking about. If you grab a bicycle, for example, and grab a motor, but disconnect the motor and connect it to the bicycle, the movement of the wheel is going to be generating this. And there's something we're going to see in the magnetism unit, that when you have movement, this is an interesting concept. Again, we're not going to be seeing it yet, but if you have a magnetic field, and imagine a magnetic field is this invisible field, and you grab something metal and move it, that movement is going to generate an electrical current. So it's kind of like a lot of magic experiments came out of doing that. So this is not actually what's happening, but imagine that you have a river that's flowing. This is an analogy because with water, it doesn't happen, but it does happen with magnetism. Imagine that you have a river that's flowing. And the river is generating a flow. And imagine that you had a pipe and you put that pipe close to the river, and magically water is going to start flowing through the pipe. Well, with water, that doesn't happen. With electricity, it does. If you have a flow of electricity, that generates a magnetic field. If I grab a conductor and put it close to that magnetic field, a current is going to be induced. So all of those effects, basically, if I, depending on the mechanism I use, I can connect that to a bicycle, and out of that I can generate energy. I'm going to say something that's probably not going to be, but I think that was probably kind of a gimmick for the concept, because I don't know how many bicycles
I know it wasn't the only energy source.
No, yeah, obviously, because you can't power a concert.
No.
But yeah.
Probably less than 1% of the.
Yeah.
That's so if you were attending the concert, you could do that?
Yes.
I'm not gonna pay $400 for a Metallica concert, so I ride on a bicycle so they can play their guitars. You do that every day. You don't want to do. You don't want to pay money. They should pay you for that.
Ajá.
Probably a very small.
Es que también decían de que, ay, se agarró
Because I mean, it seems easy because of the bicycle, actually to generate energy, for example, light a light bulb or whatever, you need a lot of kinetic energy, you need a lot of movement. That's why you need the thermal electric energy, whenever there's a thermal electric deposit that's important, dams, etc. Now, there's a thing, so we talked about voltage and we talked about current. We talked about voltage and current. There's something that relates voltage and current. That relationship between voltage and current is called resistance. Okay? It's called a resistance. Now, the concept of resistance is actually very, very simple. I think it's very simple to understand. When I say the word resistance, what comes to mind? Thor, obviously, resist Thor. It's resist Thor. The Avenger who blocks the path. So resistance is something that's going to oppose, right?
Yes.
So if you have a tube or I probably this will help. When you're drinking from a straw, so for example, Andrea, in that, that's a metal straw, right?
Yeah.
You can't bite it or anything like that. But imagine that it's a plastic straw. And I don't know if any of you guys are like myself or my daughter, that we bite absolutely everything. So the straws are all, so instead of having a normal flow, we want to have that like, we really don't want to work for it. What happens when you bite the straw and you're pulling for the liquid? You need a little more energy to pull it through, right? Why is that than the normal straw? Why is that? Because when you generate a constriction, it's the same amount of water that's going to flow, but you need more energy. Is that clear? Yeah. It's the same amount of water. So you're going to drink half a liter of water, and you're going to be sucking it through the I don't know what I was talking about, the straw. And you're going to take a certain amount of time if the straw, and a certain amount of energy if the straw isn't compressed. But once you compress the straw, you're going to take more time and you're going to need more energy.
Like
No, go ahead.
Like when you are trying to sip from the stir.
Yeah, and that's another very good example. You've seen those straws that are a spiral.
Yeah.
That's actually a better example of a resistance. The straight straw has no resistance. Yeah. There's nothing opposing the flow. But what Giselle just said, the curly straw, the curls are opposing the straight flow of the water. So that's a clear example of a resistance. The curls in the straw, that's something that's resisting the flow of the liquid. Well, over here, it's the same thing. There are going to be certain materials that, or certain materials, certain elements that when I'm passing an electrical current through them, are going to generate an opposition to the flow of the current, and that opposition is called resistance. Okay. Now, resistance. Everything has a resistance, or everything can have a resistance. Okay. But the property. Remember that in the capacitance is, because that's going to be an exam. What are the three factors that affect capacitance? The area, the distance, and the dielectric. Okay. So, but the distance and the area are geometric properties of the capacitor. The dielectric is a material that has a physical property that's called permittivity. Okay. Something similar is here. Everything has a property that's called resistivity. Okay, and the resistance of something is going to depend on the resistivity and the geometric properties. So if I have a cable, the resistance of the cable or the metal length of wire or cable or whatever, is going to depend on the resistivity, and it's going to be directly proportional to the length and inversely proportional to the area. And so there are going to be certain elements that have a certain resistivity. Depending on that, it's going to be the geometric properties is going to be the resistance. The physical element, remember that we talked about capacitance, but the physical element was called capacitor. I do find it important to make the distinction. It's the same thing here. The parameter we're going to be using is resistance. But once we put that in a circuit, the physical element is called a resistor. Okay, a resistor or resistor. And the symbol, going back to the analogy that Giselle made of the straw, it's kind of like the straw. The symbol of the resistance is this line that suddenly is cut up into little spikes. Okay.
That looks like the straw.
That looks like the horizontal swirling straw. The thorn. This one here.
Holding the straw.
I would have loved to have been the one who thought about this, but it's actually a meme that you can find.
Yes.
Online.
And they are also
Yeah, there's a bunch of things where they did that. Is everything okay? Oh, you hit the. I thought you were demanding something from Diana. Like, no. Okay. At the end. Okay, so how is that relationship given mathematically? It's actually a very simple relationship. And actually remembering the triangle, because remember that you guys might do your study, you're going to be doing your study guides and your formula sheet for all units. You can actually draw the triangle, and the triangle gives you all the formulas you need. So, and actually the triangle drawn this way with voltage on top, resistance on the bottom, and oh, I forgot to mention, resistance, the units of resistance are named after Mr. Ohm. So the unit of a resistance are ohms, okay? They're ohms, and they're usually represented with this omega Greek symbol. This is the representation of resistance. And so the triangle gives you the different formulas.
What was it?
Excuse me.
The amperes
Oh,
was
current.
Why is it represented as an I? The amperes.
That's a good question.
Because it's area.
Could be. It could be.
There's also other stuff.
That's a very good question. I don't know. So Ricardo's actually asking an interesting question, that why is current is usually represented with an I, but why is that? I'm thinking, and I'm totally guessing totally that maybe it's because these scientists were usually not, or not necessarily all these scientists were English speaking scientists. Some were French, some were French, some were German. So I don't know if maybe Ampere or God, maybe Ampere, I think he's French. So I don't know if maybe the I comes out of
Yes, but
like courant. I don't know. Maybe, I don't know. I think he is French. I think. It wouldn't translate to current in French. So that's, I'm gonna research that. That's a good mention. So coming back to this, the triangle gives you all the formulas. So voltage is going to be equal to the multiplication of ohms and amperes. Current is going to be voltage divided by resistance, because voltage, and resistance is voltage divided by current. So the triangle gives you all the combinations of the expressions, but the most common one is V equals R multiplied by I. It's amperes, it's current, electrical current. It's represented in amperes. And these are just some examples of the analogies between water and electrical current. So if we're going to be making the analogy, just for you guys to remember, the water or the fluid is going to be. Excuse me? I could ask a question in the exam where I could ask, tell me or how would you relate the concepts of relating to electrical circuits to fluids? And it's very simple. So water is the charge, pressure is the voltage, and the flow is the electrical. You can't have flow without pressure. You can't have electrical current without voltage. It's the, I don't know if you've done this, but I hope you have in your childhood. But if you've played with hoses,
Yes.
with water, that's really fun.
Yes.
My grandfather had well, I can't call it a vineyard because we didn't keep wine, but they had they grew grapes all season long. So grapes and then raisins, and they sold them. And so when I was a child, I remember us having every Sunday going to my grandfather's house, and every other Sunday we would have like a carne asada in the ranch. By the way, when I say ranch, it's not, we didn't have cows or anything like that. It's a ranch that had to do with agriculture. And there were these huge industrial hoses to water the plants there. And I remember that my cousins and myself, we just made this huge hole of mud, and we just had fun with the water hose. But it was this industrial pressure of the hose. And I remember that was really fun. We used to swim. I don't know how to swim, but we used to water in the canals and all that. And I mean, my parents are good parents, but right now that would absolutely not be allowed because it would actually even be,
Very dangerous.
it's dangerous, and it's even unhealthy to be covered up with water that they're using but it was extremely fun. And we ended up all muddied up. But if you've had fun with water hoses, you know that you've got the hose and there's certain water flowing, and then suddenly I'm putting water on everybody here in the front, but then I say, oh, I want to put some water over where Juan Ignacio is. So what do? You squeeze it, and the water comes out a little stronger. And I don't know if you've done this experiment where
Put your finger, so.
the space where the water's coming out, you're reducing it. That's generating a resistance. But I don't know if you thought about this example, but let's say you've got two buckets, and you've got two hoses that are exactly with the same flow. And so one is filling up one bucket and the other is filling up the bucket, but wants to fill it up quicker. So the person compresses the flow. Is it going to fill up quicker?
No.
It's not, because it's the same amount of water coming out, just that in one, it's less water that's coming out more quickly. And in the other one, it's more water that's coming out less quickly. But the flow is going to be same, but the amount of water is going to be, the flow is going to be different, the one water is going to be the same. So that's kind of the example when we have these constrictions. This is like talking about resistance. So this is an example. So it's like the straw. We've got the straw here, and so there's less resistance in the first one. There's always going to be resistance, by the way. Even if apparently there's nothing there, we are always going to have resistance in an electrical circuit, in any component of the electrical circuit. Just that sometimes the resistance is so small that we don't have to consider it. But there's always going to be resistance. So here there's less resistance than here in the other case where I'm squeezing the straw or the tube. Notice the amount of water that's coming in is the same amount of water that's coming out. The difference is that the constriction is going to generate a difference in flow and pressure, which is the voltage and the current. Okay, so always remember those concepts.
And what is there when you your fire line? More pressure.
Yeah, basically what you're doing when you're squeezing it, you're not generating more water, but there's more pressure, therefore the water is coming out stronger, and when you hit it, it's hitting the car rather than the other foot. So yeah, that would be a good example. There's more resistance, correct. And so here is an analogy. So if we've got two tanks, the tanks have the same height. The pressure is going to have to do with the height, because somebody talked about gravity. Depending on the height is the amount of pressure that's being generated. So the two tanks have the same height.
Yes.
That would mean that they have the same voltage.
Yes.
Saying that in the analogy.
Yes.
Depending on the length or the constriction of the tube, the constriction of the tube would be the analogy to the resistance. And the flow would be the amps, okay, or the current. So there's going to be a different amount of flow in the constriction. There's going to be less flow than in the one that's less constricted. And there's going to be a relationship between these two. So if the height is 1 volt, and I say that the constriction is 1 ohm, because of Ohm's law, that means that the current is 1 amp. If I constrict or I double the resistance, what happens to the current? The current goes in half, because it's a linear relationship. Yes. Resistance? Yeah. There's a direct relationship between flow or electrical current and resistance. The more flow, it means that you have the less resistance. Okay? Or the more current, it means you have less resistance. The less resistance, it means the less current, it means that you have more resistance. Or that's assuming that the voltage is the same. Okay. Now let's assume that the current is the same. If you have let's assume that the resistance is the same. What's going to make the current change? The amount of pressure or the voltage. So there's always going to be that relationship. But the important thing here in this example is that the relationship is linear. So again, if I multiply the resistance by 2, the current is divided by half. If I divide the current by half, the resistance is multiplied by 2. It's going to be linear, which is useful. Okay. Let's do some quick exercises. Look at those. Let's do these quickly and
Can I say that first?
from the what? Why the homework? No, this isn't homework. No, well, we're gonna do them. But yes, you can.
Can I read that first?
Sure. Go ahead.
From the data video that's left.
Yes, go ahead. Let me just, while I set this up.
Ohm's law. Ohm's law states the relationship between electric current and potential difference. The current that flows through most conductors is directly proportional to the voltage applied to it.
Correct. And that is the definition of Ohm's law. You can state Ohm's law by the formula. You can express it like he just said, or you can actually put the triangle. If we're going to do it as if we're going to do it as an expression, let's say that this were a question in the exam. There's many ways to answer this. So we could draw the triangle if we want. So state Ohm's law. Let's say that we don't want to write a definition. We could just say that. Yes, go ahead. Voltage equals resistance and current. Yes, you can, this is gonna, all of this is gonna be in the presentation, okay? But I'll just rewrite that again. And another way of representing this, if we want to represent it as a, could you read what again, Lisa, the definition, please?
Yes. In the beginning.
I think the second paragraph where you said that the current is.
that goes through most conductors is directly proportional to the voltage applied to it.
Current is directly
To the voltage.
proportional to or we could actually say that same thing the other way around. Voltage is directly proportional to current. It works both ways. Voltage and another way of saying it simply V equals R times I. Any of those, if this were a question in the exam, any of those three things would be valid. There's three different ways to represent Ohm's law. The relationship triangle, current is directly proportional to voltage, voltage is directly proportional to current, or the expression V equals I, R times I, or R, or I times, R times I, or I times R. Yes. Okay, so the rest of the questions are direct applications to Ohm's law. They're very simple. If I have a 5-volt power source and I connect that to a 10 ohm resistor, what is the current going to be? Well, you just directly apply Ohm's law. If we look at the triangle, current is going to be equal to voltage divided by resistance. So I've got 5 volts and I've got 10 ohms. That would give me a current of 0.5 amps. Okay, let's look at the third one. It says a 2.2 kilo ohm resistor has a 15 milliamp current. Find the value of the connected voltage. This is important. The same way before, we were talking about charges were microcoulombs, right? And then microfarads were capacitance, micro, nano, etc. And remember that in the calculations, if you don't consider the micro or the nano or the whatever, the times 10, etc., there could be error. Something that's going to be happening here in the values that we're going to be talking about. Usually voltage values are going to be in the, I'm going to say normal range, 10 volts, 12 volts, 30 volts, etc. Current for these exercises, or what we're going to be seeing in this in this learning module, are going to be small values. They're usually going to be in the milliamp region. Milliamp. So for example, 0.5 amps would be 1, 2, 3, would be 500 milliamps. Okay. But notice that in this calculation, this is less than 1. So it's a small, the current is going to be a small value. And usually the values of resistance are going to be very high values that are going to have multipliers. So be very careful when you're doing calculations. We're usually going to have kilo ohms, mega ohms, okay? And so be careful with that. If it's kilo, it means it's multiplied by 1,000, usually. Not usually, it's multiplied by 1,000. That's kilo ohms. That's a K there. So mega would be multiplied by 1,000,000. And so if we want the voltage, it's going to be equal to R multiplied by I. And so the resistance is 2,200 ohms, and the current is 15 times 10 to the minus 3. Very important to consider the multipliers there, okay? And so please do that calculation. 2.2 times 1,000. So how much is that voltage calculated, please? 33, correct. Okay. And question number 4, it says a circuit contains a 12-volt battery that's connected to a light bulb having a resistance of 5 ohms. So find the current. So it's same as the problem number 2, current is going to be equal to voltage divided by resistance. It's a 12-volt battery, and this is 5 ohms. It would be, I believe so. 2.4 amps. And the last one, well, before we go to the last one, I'm sorry if I'm not too quickly. Any questions with these 4? That's just direct practice of Ohm's law. We're going to be complicating things later on. Right now, it's simple applications. For question number 5, it says we have 2 batteries. One is a 3-volt battery, and one is a 12-volt battery. And the batteries, it says that they're connected in series. And as well, they're connected to a 1 kilo ohm resistor. So, if the batteries are connected in series, what does that tell me? At least for voltage, the same principles that we saw with capacitance apply. So if I have something in series, what happened with the voltage in series? Well, if I have one voltage source and I have something in series, it's distributed, correct? But let's think about it the other way around. Now I have 2 power sources that are connected in series. What would happen with the total voltage?
Oh,
They add up. So if I have 2 power supplies that are in series, that would mean that the voltages are going to be combined. So for this example, and I'm gonna do this one here.
Because of the guys who have the voltage, not the one who is in it.
I didn't understand why.
Oh, always the voltages in series are always going to be distributed. Okay, so if I have a power source, a 10-volt power source, and I have two elements, those 10 volts are going to be distributed between those elements.
It's the same, right?
No, the voltage is different.
It's different.
It's different. And so if I have two power supplies that are different, and I connect them in series, the combination is going to be the addition of these two. Okay? And so the total voltage is going to be 3 volts plus 12 volts. The total voltage in this case is going to be 15 volts. The current is going to be the total voltage divided by the resistance. In this case, the current is going to be the 15 volts divided by the resistance, which is 1 kilo ohm, which is 1,000. And so in this case, I is going to be 0.15. Amps, okay?
Así no iba a ir. Así voy a ir.
Okay, was it color code?
We can wear green.
No, they can wear whatever they want,
I
but
know
not
I-
green because I'm wearing.
Yo así voy a llegar.
Ay, a mi pizza de queso ya.
Por eso decía que con bolsos.
Okay,
No puedes comer.
questions with these 5 problems here that is almost all. Nope. Okay. I'm not gonna remove them.